Great.
Hi everyone. In this video, we're going to look at some methods of exploratory data analysis. So we're going to start with a discussion of univariate statistics and visualizations, so numerical summaries that describe a single variable and graphical representations of a single variable. And then we'll also talk about bivariate statistics and visualizations, so numerical summaries of two variables, the combinations being a categorical and quantitative, or two quantitative, two categorical, etc., and also graphical representations for those. We'll look at briefly a little bit of multivariate statistics and visualizations as well, but primarily these univariate and bivariate statistics, as these get you very far in data analyses, and it's the majority of what is done. And in this activity, we're going to be looking at a real-life data set on the Palmer penguins, they are called. So this data set is a collection of measurements on 344 penguins from 3 different islands in the Palmer archipelago region of Antarctica. These were collected in a research study and graciously made available by Dr. Kristen Gorman and the research station team that collected this data on these penguins. Okay. So some of the variables we're going to be looking at in this data set are listed in this data dictionary here with the variable name and then the description. So measurements of the penguins are given for the most part in millimeters. Their body mass is measured in grams. Okay. So here are the quantitative variables we're going to be looking at along with year. And then we have some categorical variables. The species, the penguin is from the island the penguin was found on, and the sex of the penguin. So exploratory data analysis very generally is this collection of methods consisting of descriptive statistics and data visualizations, which are used to explore or improve understanding of a data set. Typically, EDA is only conducted once a data set is cleaned or organized and in a format that's ready for analysis. Although sometimes it's done before that step even, in which you're just getting acquainted with the structure of the data set as well. EDA is a fundamental skill of being a good data scientist or statistician, and that in order to conduct good predictive modeling, to use effective machine learning models, for example, one should have a good, sound procedure for conducting exploratory data analysis first. EDA is important because it helps us identify extreme or unusual values in our data set. Sometimes these are due to miskeys, or they can just be unusual values, which we may consider excluding if we're trying to make accurate predictions, depending on the context. And we refer to these extreme or unusual values as outliers in statistics. It also helps us, conducting EDA also helps us explore patterns of missing data potentially. So it's always good to look out for missing values that are unknown in our data set, as many methods of analysis and predictive modeling often relies on this assumption of no missing data, which is often not the case. And so these should be carefully noted and potentially handled in an appropriate way. EDA is also useful for formulating questions of interest or hypotheses about our data set that maybe we didn't consider before. Sometimes these visualizations can make us realize there might be some type of pattern in the data that we didn't expect, and so we can investigate that further. And for the most part, EDA is just important for generally improving the understanding of our data. Maybe we thought a relationship would be there, but it doesn't seem like that's happening. Maybe we realize there's not as much data on subgroups as we expected. And so EDAs, where we can sort of catch all of these things very early on before getting into extensive analysis or modeling. So as I mentioned, there's two main components to exploratory data analysis: calculating descriptive statistics or numerical summaries about a data set, and then also making graphical representations of our data, what we call data visualizations. So starting with these numerical summaries, which we call descriptive statistics. Descriptive statistics are things we calculate about our observed data set, which in statistics we call the sample. This is analogous to inferential statistics, which are calculated for a population, where typically we don't have data on the whole population that we're interested in, just a sample of data. Okay. Data visualization, this process of graphically representing our data, allows us to efficiently present data in a compact space. So sometimes data can have hundreds, thousands, or even tens of thousands of rows, potentially dozens of variables or columns. And that scale of data is nearly impossible for us as humans to understand and condense into meaningful takeaways just looking at a huge table of numbers. So data visualizations can allow us to condense this information down into some main takeaways in such a way that we as humans, as people, can come away with an understanding or a main takeaway. So in that regard, it efficiently presents data in an understandable and coherent way for us, and specifically for our target audience. So sometimes you're making a data visualization for a fellow statistician or data scientist, and this would likely be a little bit different than a data visualization that you make for someone without as much of a quantitative background. So it's always good to keep your target audience in mind. Are you presenting to a business manager with no statistics background, or are you presenting to your data science manager? You would likely show some different plots as you did that. Data visualizations should also serve a clear purpose. The goal is that you communicate an important aspect about your data, and it's clear what you are communicating. You shouldn't leave your viewer wondering, what was I supposed to learn from that plot? Or what's the main takeaway? And the last thing is that data visualization should not distort or hide aspects of the data. It should be true or faithful to what the data actually shows us. So there's some general best practices for data visualizations that this team at Novartis made up. And I think some of these were really good. And they apply to when you're using R, but also any other programming language to make different visualizations. So you can check that out. But we'll proceed with looking at some univariate descriptive statistics here. So numerical summaries for one variable. When we have one quantitative variable, here are some of the most common statistics that are calculated. So this is an example of summary statistics, a table of summary statistics for the flipper lengths of the Palmer penguins. These are all non-missing. We have values for all of these, even though not every penguin had a flipper length recorded for it. That is, there is some missing values in this data set. Missing values instead of a number in R will show up as NA for not a number or not applicable. I'm not sure which one it stands for, but that's how missing values are encoded. Since there were some missing values in this data set, these statistics were calculated with those values being removed. That is the most common approach for handling missing values, which generally is okay if there's a small number of missing values in your data set. Say if less than 1% of values are missing, for most data sets, this approach of just excluding them in the calculation of statistics is okay. But it's always good to check. Sometimes you can have as high as, say, 50 or 60% of missing values in a data set, in which case the statistics that you actually are able to calculate might be misleading or not representative of the population you are interested in. So it's always important to be careful of that. For example, when I was in a data science job interview and I was given a data set to conduct some exploratory data analysis on, they sneakily put one of the variables as having over 90% of missing values. And they made it such a big data set, you would have to, it would be hard to spot in the data by just opening it up in Excel or something like that. So it's always good to look out for those things. And it's not that it's an easy thing to handle, but it's always good to make note of it, that you are aware that there's some potential issues with that variable, if that's the case. That's what those people are looking for, say, in a job interview test. They just want you to make note of it. Okay. Missing data, like appropriate methods for handling this issue, is a complicated issue in itself. And often there can be an entire semester course just on handling missing data. So I found this chapter 17 of this freely available textbook, Regression and Other Stories, which has a great discussion of methods for handling missing data. It's a bit more complicated and at a slightly advanced level, but I think it's a very useful discussion of how to handle missing values for those who are interested. Okay, so focusing on this data set, let's think about, based on this table of summary statistics, what are the largest and smallest flipper lengths? It's always important to give units of measurement when you give these values. So in this case, it's millimeters, which is given by the minimum. Given by the maximum. Okay. So the min gives the smallest value of a data set, the max the largest. If we want to describe the middle of a distribution of values, the mean and median are both measures of center, or measures of the middle of a data set. These are commonly mixed up for people who have not taken a statistics course. Some people in everyday language use the terms mean and median interchangeably, but they are different statistics. As we can see from this table, these are different numbers. They can be similar, as they are in this data set. They can also be very, very different. Okay, so they're not the same thing. Here, the mean again, given in millimeters. And then let's look at the median. The median is 197. Okay. So the median is 197, and the median can be interpreted for a data set. So that's how we can interpret the median. It's in the very middle of the data set in terms of percentiles. The mean is more sensitive to outliers than the median, and the median is more robust or less sensitive to outliers than the mean. This is why typically for data sets or variables with extreme outliers, the median is a better measure of center or the middle. So you'll see for housing prices, for income, for example, those are commonly reported by giving the median rather than the mean. Because for income, for example, Jeff Bezos has a crazy large income, and so his value would pull up. If we were looking at the typical income for a United States citizen, his income would pull up the average extremely high. And it might pull it up so much that it's above potentially every other US citizen except himself. And so in that case, it's a very extreme example, but it is possible. And in that case, that's not a very good measure of center if the mean is above every single value in the data set except one. Whereas the median will always have half of US citizens below that number and half above that number. Okay, that's why for variables or sets of values with outliers, the median is a better measure of center. Maybe wondering, why do we even use the mean then? Well, the mean has some very nice statistical properties, some nice theoretical properties that the median doesn't have as much, but for describing the middle of a data set for everyday things, the average is the median can be often more useful. Okay, so talking about the quartiles, Q1 in this data set, the first quartile, and Q3, the third quartile. So Q1 is 190. Q3 is 213. And here's how we can interpret these values. Q1 is the 25th percentile, which means that 25% of penguins had a flipper length of that value or less. Q3 is the 75th percentile. Some other statistics that we can calculate, as we're done in this data set, we have the standard deviation here and the range. These are both measures of spread or measures of variability. They describe how spread out values are for a variable in our data set. Just like the mean is more sensitive to outliers than the median, the range is very sensitive to outliers and more so than the standard deviation. There's also a statistic called the interquartile range. The interquartile range, commonly denoted as IQR, is equal to Q3 minus Q1. And the IQR is more robust to outliers. So robust is the opposite of sensitive in statistics. And the range is equal to the difference between the max and the minimum, as a reminder. Okay. Other statistics for univariate analyses for one variable. Commonly for a categorical variable, we give a table of counts. So a frequency table, sometimes this is called. This is telling us there were 152 Adelie penguins in this data set, 68 chinstrap, and 124 gentoo. And we have the number of penguins on each island, the number of penguins of each sex, whether they're female or male. Okay. So which penguin species had the most? the Adelie penguins. Adelie penguins. And that was n equals 152. Which island had the most? Bisco. Bisco had 168. And then are there more male or female penguins? In this data set, there are more male, 168. So notice that there are some missing values. There was 11 penguins which had data, but did not have the sex recorded for that penguin for some reason. So we will just exclude those from our discussion here. Fortunately, it's not a very large number relative to the size of our data set. Okay. So those are all univariate statistics for categorical variables and quantitative variables for the penguins data set. You can also look at visualizations here. So to visualize a single quantitative variable, a histogram is a common visualization. Histograms have the frequency or percent as the y-axis and the actual variable values as the x-axis. Okay. So from this histogram, we can say so it's bimodal, it has two peaks here. And the middle, if we picked out the middle of the data set, it's somewhere here at this 200 millimeters. Okay, this peak is taller, so it would pull the middle a little bit more than this peak because it's shorter. So it would end up about 200 millimeters, which we recall back to the mean and the median from the numerical summaries. That's about where the mean and the median were. They were about around 200. A box plot is another way to visualize a single quantitative variable. The box plot and the histogram both show slightly different things. You can't tell if a distribution is bimodal from a box plot or not. So these are the same values shown in this box plot. You can see the bimodalness of the distribution here in the histogram much better. Box plots, though, are useful in that they quickly communicate many different statistics. So for example, based on this box plot, we can say the median, which is given by this line right here through this box. The median is roughly 195 or 200 millimeters. And we know it's exactly 197 from the numerical summaries, but here we can just tell that just from this plot. Q1 is about 190. So the bottom line of the boxes always gives you Q1. Again, if we looked at the numerical summaries, we could probably see, oh, Q1 is exactly 190. Okay. Q3 is given by the top line of the box. Okay, so that's about 212. Q3 is about 210 or 215 millimeters. Yep, you can see that's the case again. All right. And then the range is given by this span here. The highest and lowest point, the difference between those. Okay, so that takes a little bit of thinking. So the max, let's maybe first piece out what the min is. The min is about 171. We'll just say 170 millimeters. The max is about 230. And so the range is about 60 millimeters. And let's see how that holds up in the numerical summaries here. Yep, the range is about 60. We had the max being 230 and the min being 170. Okay, so roughly correct. We have to eyeball it somewhat from the box plot, but the box plot communicates a lot of those values to us here. So it gives a lot of good summary statistics in a graphical representation. Okay. Are there any outliers present? So we'll say no, there are no apparent outliers present. All right. So for these were visualizations for a single quantitative variable, a histogram, and a box plot. For a single categorical variable, a pie chart or a bar chart is commonly used. Here we're just going to look at a bar chart because in my opinion, and I think many other statisticians feel this way, they communicate information a little bit more efficiently, a little bit more quickly than a pie chart. But they show the same information and are both technically correct visualizations. So certainly there's nothing wrong with making a pie chart if one wants to. But okay, so from this pie chart, we can quickly see most penguins were Adelie penguins in this data set, and the chin strap penguins, yeah, at least. So it allows us to quickly see that, especially if we sort the bars based on height. Adelie was most common, chin strap the least common, and Gen2 in between. So frequency is the same as the count, the number of observations, or in this case, the number of observed penguins. All right, so moving on to two variables, or what we call bivariate analyses. We'll start with two quantitative variables. So descriptive statistics for two quantitative variables, the most commonly used statistic is the sample correlation coefficient, commonly denoted with a lowercase r. The correlation coefficient, sometimes called Pearson's correlation coefficient, describes the strength and direction of a linear relationship between two variables. Correlations always are bounded between -1 and +1 inclusive, with values closer to -1 suggesting a stronger negative linear relationship. Emphasis on it must be linear. Values closer to 0 indicating a weaker linear relationship, and closer to +1 being a stronger positive linear relationship. Correlations are very widely used. Sadly, in many ways that are not appropriate or that are misleading, because they're very simple to calculate, but there are a lot of restrictions in their interpretability or meaningful in their meaning in many situations. So the biggest caveat with correlations are that they only measure straight line relationships, or they only quantify the strength of straight line relationships. But many relationships are non-linear. So for example, maybe we have axes like, so we have two variables, x, and we have y, and then we have data points Okay, like this. Okay. In this case, X and Y seem like they do have a relationship. Okay. They certainly are informative of each other. If we tried to draw a line through them, there's a clear trend, but it's not very linear. It's not a straight line relationship. So the correlation would not, just reporting on the correlation coefficient for like this data set, it would likely be close to 0 for the correlation between X and Y. Because if you drew one straight line through this set of values, it would probably end up being pretty flat, indicative of there being no relationship, no linear relationship. Okay. So correlation coefficient is very limited in that regard, but still very useful. Just that needs to be kept in mind when looking at those types of things. Okay. So that's one caveat with correlation coefficients. Another caveat is that even if it is linear, a strong correlation between two variables does not imply causation. It does not mean that they're causing each other or affecting each other necessarily. So a good example to show this point, if you recorded ice cream sales at Daytona Beach in Florida and looked at how that correlated with the number of monthly shark attacks. So if you calculated the correlation between those two values, you would see a positive correlation between those things. And so if you ignore everything else in the world, this may seem to indicate that more ice cream is attracting sharks, and we should potentially consider getting rid of ice cream to save people from shark attacks, right? But that's not the case. This is due to what we'd call confounding variables. So in this example with ice cream sales and shark attacks, there is a confounding variable or an additional variable that's distorting the relationship between the ones that we're analyzing. In this case, it is temperature, right? The warmer it is outside, the more people are buying ice cream, and also the more they're going to the beach, so that there's more potential for shark attacks. Okay, so temperature is correlated with ice cream sales and likely has a causal relationship, but it's not likely that ice cream sales have a causal relationship with shark attacks. Okay. So confounding, sometimes like in this case, using some common sense, it's very clear that there's a confounding variable. But unfortunately, it's not always the case that when you're analyzing data, it's clear that you have a confounding variable or multiple confounding variables potentially present. And another issue is that you might not even have it recorded in the data set. Like in this case, if we didn't record temperature and we weren't aware that that was something that may interplay with these variables, it's really hard to know that that's something to look out for if it's not even in the data set. Okay. So confounding variables are tricky, something that should always be considered as a possibility, especially if you're seeing relationships that are maybe surprising or unexpected. But assuming and proceeding with using this correlation coefficient cautiously, we can look at it for the pairs of variables in this penguins data set, so the pairs of quantitative variables, because the correlation coefficient is only for two quantitative variables. You can't calculate, or you should not calculate, the correlation between a categorical and a quantitative variable. Another common mistake. So here, this table gives we call it a matrix, a numeric table. And it's symmetric in that if you take the first row in the second column, that's equal to the second value in the first column. These are equal, and so on. This is giving, for example, the correlation between bill depth and bill length. Here is the correlation between flipper length and bill depth. And then you'll notice that on the diagonal is 1 always. So here's the correlation between body mass and itself. The correlation of a variable with itself is always equal to +1. So which variables have the strongest correlation? Not counting the variables with itself. Okay. So the strongest is not necessarily the most positive. You can have a strong negative correlation. So let's look at what the biggest value is. Looks like 0.87. Okay. So body mass and flipper length. Are equal to 0.87. Right, so to emphasize again, it's not because it's the largest positive number, it's the largest in absolute value among all of the correlations. This correlation, for example, is stronger than this correlation, even though it's negative. Okay. Which variables have the weakest correlation? So on that note, this is close, but there's a 0.04 here. So that looks like that's our smallest. Yep. So body mass and year. So body mass and year have the weakest correlation, and it's 0.04. Okay. So that's a common statistic we look at for two quantitative variables. For one categorical and one quantitative variable, commonly what's calculated are what we call group-wise summary statistics. So essentially the same summary statistics as before for one quantitative variable, but now for each of the different groups or levels of a categorical variable. Okay. So based on this, for example, we have the mean flipper length of the chin strap penguins, the median flipper length of the Gen 2 penguins, and so on. So from this, we can tell which penguin species typically, so getting at its middle or typical value, had the largest flipper lengths. So that would be which one had the largest mean, essentially, in median. That looks like the Gen 2 penguins. The maximum would not be a good measure of which one typically had the largest flipper lengths, because that's just one individual penguin that had this value. Which penguin species had the most variability in their flipper lengths? Recalling back to which statistics measure variability, here the range and the standard deviation, as well as the IQR. Okay. So let's look. Based on the range and standard deviation, okay, so the range, the Adelie penguins had the biggest range. The chin strap penguins, however, had the largest standard deviation. So let's make note of that. So the Adelie penguins All right, and let's see which one had the biggest range or IQR. And the IQR is the difference between the Q3 and Q1. Okay, so here that looks like it is the difference between this number and this number is 9. The difference between this number and this number is 10. And the difference between this number and this number is 9. Okay. All right, so 10 is the biggest. Okay, so chin strap penguins, it's all very close though. Chin strap penguins with a IQR if you just cited the range here and said Adelie penguins have the most variability because they have the largest range, I would accept that too. But good to do a thorough analysis here like that. Okay, so IQR was biggest for the chin strap. All right. When you have two categorical variables, a common set of numerical summaries that are calculated is the counts of the cross section of the two variables. Okay. So this, for example, is the number of Adelie penguins found on the Biscoe Island, 44. All right. And then we also have the number of Gentoo penguins on the Biscoe Island. Note that there were 3 species and 3 islands. So if we had the cross section of all of those, we should have 9 rows. There's not 9 rows here because values that had zeros are just excluded from this table. You could have rows where the counts are 0. And that's how we have a table later, actually, in this activity. But the table could be shown like this as well. So was any penguin species found on more than one island? Yes. Adelie penguins were found on 3 islands. Okay. Biscoe, Dream, and Torgerson. So they really got around between the islands. Okay. How many penguins were found on the Dream Island? Okay, so we got to add up the 2 numbers for Dream. So 56 and 68. And so that gives us 124, I think. Great, 124. Perfect, okay. Then for visualizing the relationship between 2 variables, and specifically 2 quantitative variables, the scatter plot depicted here is the best visualization, the most commonly used one. Okay, so here we're looking at a scatter plot between the flipper lengths of the penguins and the body masses of the penguins, where each point is a single 2-dimensional measurement indicating the flipper length and the body mass of that particular penguin. In regression analysis, which we'll be looking at, that involves estimating a straight line of best fit, and we can plot that straight line of best fit from a regression model on a scatter plot as well to show the trend or pattern in the data. So based on this scatter plot, for example, we can say there is a positive, moderately strong relationship between So it's positive because the line has a positive slope. As body mass increases, the flipper length increases, and it's moderately strong because the points generally stick to that trend. There's some bouncing around, there's some variability about the line, but it's not a large amount. So we'll just say moderately strong and positive relationship. Okay, so that's the go-to visualization for two quantitative variables. For one categorical species in this case and one quantitative, a common visualization is side-by-side box plots. So based on these box plots, we have that Gen 2 penguins. So that's what we can note. We could note roughly what the medians are equal to for each group as well. We could note the Q3, Q1, Q3, Q1, the IQRs for each group. Yeah, so I guess we can note that IQR values are roughly the same for each penguin species. Okay. So the variability looks pretty similar within each group. And this is for when we have one categorical variable species and one quantitative variable flipper length. If we have two categorical variables, this gets a little bit more dicey. One common visualization that people use, although I think is less and less commonly used more recently, is the clustered bar chart, where essentially you split up a bar chart for each level of an additional categorical variable, in this case, the sex of the penguin. So here is for example, this height of this purple bar gives the number of female chinstrap penguins in this data set. And then this is the number of male chinstrap penguins in this data set. Clustered bar charts are okay. You'll see them, they're decently often used. They do make it a little bit difficult to compare across groups, especially as the number of subgroups increases, which can happen quite quickly. To be honest, it's just not the easiest to visualize two categorical variables at once. So we're sort of just trying our best if that's what we need to do. An alternative type of plot, which I've seen more recently, just within the past few years, although it's certainly been around longer, but this is a trend I've noticed. Some people have indicated their preference for this dumbbell plot over the clustered bar chart. So this is showing the same information, but instead of the height of the bars, there's a point indicating the frequency of each subgroup. I liked this because I think it makes comparisons across groups a little bit easier. So here, for example, we can see quickly that, and efficiently, that there's the same number of male and female chinstrap penguins in this data set. There's the same number, roughly, of male and female Adelie penguins in this data set. And then we can also see that there's slightly more male Gen 2 penguins than female Gen 2 penguins in this data set. Whereas gleaning that same information, getting that same information from this clustered bar chart was not as easy. It's a little bit more difficult to compare across the height of the bars here, for like the Gen 2, for example, but here it's easier to see this one's bigger than this one. It's marginal differences. It's not huge, but I think I was a traditional clustered bar chart user myself, and I think I may have been convinced by those who argued for this dumbbell plot. I think it's maybe a little better. But again, sort of like the pie chart, bar chart debate, neither are incorrect, sort of a personal preference. More of an art than a science, as they say. No, there's still correctness to it, but okay, so what can we say? Oh yeah, sort of what we were just saying there. So so there's several things you could say. We'll just say those, list those there. All right. Now looking at multivariate analyses, meaning multiple variables, just more generally, not necessarily just two. This again gets sort of progressively more difficult. The more variables you try to incorporate in an analysis, the more difficult it is to present efficiently and understandably in one table or in one graph. But for 3 or 4 variables, this can still be done. I would say if you start to get more than that, it probably is a good idea to just consider only 2 or 3 variables at a time. Otherwise, it's, in my opinion, gets to be too much information and it becomes overwhelming for the viewer who you are presenting it to, what the main takeaway is supposed to be. Okay, so 2 or 3 variables, in my opinion, is that happy place. Okay, the Goldilocks zone. All right, so looking at 3 categorical variables here, species, island, and the sex of the penguin, we can get all the cross sections here. And this table is including zeros this time, unlike the previous frequency table, and it's also including missing values. So for example, there was one penguin that was an Adelie penguin, and it was recorded on the Dream Island, and they weren't able to tell if it was male or female, apparently. And there were 5 penguins such that was the case, who were Adelie from the Torgerson Island, and they didn't know or didn't record whether it was male or female. Okay. And that happened for 5 Gentoo penguins on the Biscoe Island. Okay, and then there's a bunch of zeros for different subgroup combinations. This is a lot of information. Maybe good if you're showcasing the results very in detail for an analysis and sort of like appending this to the end of a report. Would I show this in a presentation ever? No way. This is way too much information for like a presentation or a slideshow. Okay, but it's something we can calculate. When we're doing visualizations, when we're creating visualizations, we can add additional variables or additional dimensions to a visualization using what we call aesthetics. So for example, coloring the points, we can use the color aesthetic to show an additional dimension in a scatter plot here, where we're showing the species of each penguin. So now each point, for example, this point is purple, so we know it's a chinstrap penguin, and we know its body mass and its flipper length. Okay. So here, oh, from the scatter plot, we can tell Gentoo penguins typically had the largest body masses. Okay, so if we're looking at just the x-axis, it's like, oh, all these points to the far right are pretty much all teal, which is the Gentoo penguins. In terms of body mass for the Adelie and chinstrap, it looks like they're sort of, in terms of the x-axis here, they're pretty overlapping. So while Adelie and chinstrap penguins had similar body masses. Okay. We can also say that all penguin species had a positive and fairly linear, so fairly straight line relationship between their body masses in grams and their flipper lengths in millimeters. Okay. So if we, for example, imagined drawing a straight line of best fit within each group, we could have one for the Adelie penguins, which would maybe look like this. The Gentoo penguins, which would maybe look like this. I should have made that a little bit lower, but, and then the chinstrap penguins, which maybe look like this. Okay, so all the lines are positive within each group, pretty linear. Yeah, so that's a few things that we can take away from this plot. We can also tell like what the smallest flipper length was, about 170, and the biggest, which was about 230. Same with the body mass. The smallest body mass looks like it was about 2,900, and the biggest body mass looks like it was about 6,200 grams. Okay, so you can tell a lot of things from this scatter plot here. Alternatively, instead of having one scatter plot where you're changing the color of all the points, you can use what's called faceting to incorporate additional dimensions or variables in your visualization. So here we facet by the species of the penguin, and then we can still color it by the species as well. You didn't have to here because the facets indicate which subplot is for which species, but certainly doesn't hurt, especially if you have a, many different visualizations like a bar chart, a dumbbell plot, box plots, and you want to stick with a common theme. Like in this case, Gentoo is always teal, Adelie's orange, chinstrap is purple. If you're giving a presentation, you could keep the colors consistent to more effectively communicate the results. Okay. So here, yeah, we have this faceting, and then we can still see Gentoo had the biggest body masses. Adelie and chinstrap were similar. Okay. All right, and then we have this, we can also facet a dumbbell chart. So in this case, we're showcasing 3 categorical variables all at once. Again, in my opinion, it gets to be a little bit too much to have 3 variables, 3 categorical variables. I would maybe just stick to 2. But if you wanted to show 3 at once, this is a good plot to do that. So yeah, some main takeaways here. What can we say from this dumbbell chart? So this shows us, for example, there's a lot of zeros. Okay, and looking at like the Gentoo penguins, for example, they're all zeros except for the Biscoe Island. So we can say Gentoo penguins were only found on the Biscoe Island. That's one main takeaway for sure. Let's see. How about like Adelie penguins? Were they only found on one island? Nope, they were found on all of the islands. Okay, so but what about chinstrap? The chin strap points actually got covered up here by the Gen 2 points. So they're all 0 except the Dream Island. So chin strap penguins were only found on the Dream Island. And we mentioned this before, Adelie penguins were found across all islands. Okay, yeah, what about the distribution of the sex of the penguins within each of these combinations? Well, there's not much to take away here because I guess the main takeaway is that it's very similar, right? The number of male and female Adelie penguins is pretty much the same on the Disco Island. It's pretty much the same on the Dream Island. It's pretty much the same on the Torgerson Island. Yeah, so for the most part, the number of male penguins of each species was similar to the number of female penguins found on each island. Yeah. With the exception being there were slightly more male Gen 2 penguins found on the Disco Island. This is where, like what I was talking about, how it's hard to have a main takeaway because there's so many bits of information that are being communicated by this plot. I think it's a little bit too much, so you don't have a good one main takeaway. But if you needed to visualize 3 categorical variables at once, this is one way to do it. Okay. And so the last thing we'll look at, with this last section just being the R code for making everything that we did in this activity, the last plot that we'll look at is this scatter plot showing 3 quantitative variables. And this, similar to the 3 categorical variables, I would say you probably shouldn't do it if you don't have to, because it's too many variables in my opinion. But again, if you were showing 3 quantitative variables, we could color the darkness of the points here. The darkness of the blue is indicating the bill length of the penguin. And then it's a scatter plot, again, of flipper length and body mass. So here we can see there's darker points in the bottom. So penguins that had a smaller body mass and smaller flipper length typically had, not surprisingly, smaller bill lengths. Okay. And penguins, these are lighter points up here. So penguins that had larger body masses and larger flipper lengths tended to have larger bill lengths. Maybe not surprising, but sometimes you might see interesting patterns when you plot an additional variable like this. Okay. So as I mentioned, if you to reproduce any of these tables or plots using the Palmer Penguins data set, I provided all of the R code that made these plots here below in this R code section. So you should be able to take this code and copy it. Make sure if you use it that you need to run the code starting from the top to the bottom, and it should reproduce the plots and tables that we created in this activity. I included R comments to indicate what each piece of code is doing. So here's creating a scatter plot. Here's creating the dumbbell chart, okay, and so on. So let's go back to the top. So that's it for this activity on exploratory data analysis.